As many of you know, quantum mechanic, molecular mechanic, multiscale simulations can be a powerful way of studying the reaction mechanisms of enzymes. However, one of the big challenges that arises when working with QMMM systems is choosing the right quantum mechanics region size. In the simplest cases, those with enough experience can get a good idea of which amino acids to include by using their chemical intuition. For example, on the screen we're looking at a rendering of the protein tau D, one of the best studied non-heme iron hydroxylases. Now in the case of tau D, we can immediately identify 3 amino acids to include in the QM region: histidines 99 and 255 and aspartate 101. These 3 amino acids are obvious choices as they are coordinated to the iron center. But what about the residues in the second coordination sphere? Well, that can be much more difficult. And to solve this problem, we in the Kulik Lab have developed a technique known as charge shift analysis, which can be used to identify key amino acids that should be included in the QM region using a systematic and unbiased approach. The idea of charge shift analysis is simple. It is based on the idea that amino acids important in a chemical reaction will be involved in charge transfer with the substrate. To work with our example of tau D, that would mean that we expect there to be a charge transfer between the ligands taurine, succinate, iron, the oxo group, and the coordinating residues. Charge shift analysis gives us a technique where we can be more sure that we capture even unintuitive but key amino acids in the QM region. Now, to use charge shift analysis in its most basic form, we start with a protein and its ligands. We then perform 2 QMMM single point energy calculations. The first calculation is on the holoenzyme, which is a term that refers to an enzyme-ligand complex. This first calculation will give us the charge distribution that the enzyme experiences when the ligand is present. Next, we perform a QMMM single point energy calculation on the apo structure, which is a term that refers to the enzyme when the ligands are not present. This second calculation will give us the charge distribution that the enzyme experiences when the active site is empty. Lastly, we can easily compare the charge distributions in the two cases using a Python script provided by us at the Kulik Lab called Quick CSA, which I'll cover in detail in the next section. After we run Quick CSA, we are provided with a list of all amino acids that experience a significant change in charge upon switching between the apo and holo structures. In the case of our example tau D calculation, we find several residues that experience significant charge transfer in addition to the obvious metal coordinating residues. They include aspartate 94, asparagine 95, valine 255, and arginine 266, all of which are known stabilizers of the substrate taurine. Now, with that basic description out of the way, let's take a look at how to run Quick CSA. First, you can download the Quick CSA script by navigating to the GitHub repository davidkastner/pi-qmm. Then select code, and from the drop-down, you can select download zip. For this tutorial, you only need a few files, but this is still the fastest and easiest way to get access. Once the zip has downloaded, go ahead and unzip it by double-clicking. To find the Quick CSA script, open the pi-qmm folder, and you'll find an assortment of scripts, one of which will be Quick CSA. However, for this tutorial, we'll provide you with all the files you will need in the examples directory. To find the example directory, first navigate to the docs, then open examples, and then Quick CSA. There you will find 2 directories. The results directory shows the final file system and all the intermediate files that are generated automatically by running the script, and the starter folder provides you with the bare minimum files you will need to run the script. As you will notice, Quick CSA has been set up to handle as much of the calculation as possible. However, there are a few files that you will need to provide for your unique system. Now that we've reviewed the required files, we are ready to run Quick CSA. Open a new terminal in the current directory by searching for the terminal. You can then drag and drop the directory on the terminal icon to open a terminal at that location. Okay, now depending on what Python packages you already have installed on your system, you may not need to install anything. However, if we open the Quick CSA script, we will see that there are 3 common packages which can be installed via a conda environment: the OS package, the systems package, and the shutil package for creating and organizing the file system. For this tutorial, I previously created a conda environment called QMMM, which I can activate. Now run Quick CSA with the command python quick_csa.py. The first file you will need to provide is a protein PDB. This is the PDB that you use to set up your QMMM system and should be the holo structure. The second is the output from your QM software, which shows the calculated charges for each atom. In the case of this example, we're working with TerraChem files, which allows for GPU-accelerated electronic structure calculations. If we open this file, you will see that we have the charge of every atom in our system, which is a lot, but don't worry, QuickCSA will sort through it. Next, we will need a list of all the residues that you included in your QM region. If we open this file, we will see that it is nothing more than a simple comma-separated list on a single line. While the first two files that we looked at were for the apo structure, we will also need the same two files for the holo structure so that we can compare them. QuickCSA first prints a short description about itself, including its purpose and the required files. Overall, QuickCSA requires very little user input. However, it will first prompt you for the name of your PDB in case you have multiple that you would like to process. Once you've entered the name of your protein, press enter. The script should finish in seconds. Under the calculation section, the script will print the number of residues that were included in the apo and holo regions. The holo region should have more residues as it also contains the substrate. In the results section, it will print the name of each residue that experiences a change in the magnitude of its charge greater than or equal to 0.05. In our case, we can see that it successfully identified all the coordinating residues as well as 4 other key residues that should be included in the QM region. Now, if we go back to the folder where we execute the script, we will see that QuickCSA automatically generated 3 new folders: an input folder, a temporary folder, and an out folder. The input folder contains our original input files. The temporary folder contains all the data from the intermediate calculations performed by QuickCSA. The temp folder can be a useful resource for troubleshooting unexpected issues with your calculation. Lastly, the out folder contains the results. Here you can find the charge shift of every residue in the files that start with all, and a list of the residues whose charge shift was greater than our threshold in the files that begin with cutoff. With that said, that concludes this tutorial on performing charge shift analysis. I hope you learned something useful, and happy computing.